Okay, welcome back to class, everybody. A pretty good time to get started. So let's just briefly remind ourselves what we talked about last time. So we spent most of class doing these two things. First, we started about talking about pandas, which is Python's main method of working with data. And most data is organized in the form of a table. And pandas provides you a ton of functionality to do things like easily read in that table in most common formats. So you can read in things like CSVs, Excel files, and so forth, and many others. And then it lets you do functionality like search for a particular row. So find a row that has some value in some column, or all the rows that have some value in some column. It lets you do things like merge different tables by matching up columns. And lots of other things, index in interesting ways, and so forth. And then we spent the second part of class talking about geographic data. And in particular, we familiarized ourselves with shapefiles, which is the most common way of storing geographic data. And so you guys know now that whenever somebody says or refers to a shapefile, what they're talking about is a bunch of shapes described by a sequence of points that might be like a polygon. And then each of the polygons might have a bunch of data associated with it, right? So things like the name of the polygon, the land area, maybe if it's a geographic region, the population that lives there, or whatever other data that you want to associate with the polygon. So it's those two things, like both the shape and the data associated with it. And we saw a bunch of information on how to plot geographic data. In particular, I showed you two things. So first, there's QGIS, which is just a free software tool that's available where you can create very complicated geographic plots. But the downside of it is that it's point and click. And it is possible to program that, but it's significantly more complicated than the second tool which I showed you, which is just Matplotlib's base map module. And what we did in specific was we went over some code that I had written called geoplotter.py. And geoplotter.py, all it does is it wraps a bunch of functions that are in Matplotlib base map. So it's just like an easier way of calling a lot of the things that you would call from Matplotlib base map. And at the end, where we ended was we were just able to plot the counties of Texas onto a map. And I gave you as an exercise, I told you to try plotting Travis County in a different color on that map. Did anybody try to do that? Okay, well, then if we have some extra time, maybe we'll do it together towards the end of class. The reason I say that is because it's going to be important for your next homework assignment. We're going to do some geographic plotting for that. So the plan for today is to first spend some time going over homework 1. So generally, on the day that homework assignments are due, we're going to go over them in class, which means that it's best to turn in your homework assignment by the start of class time. So that way, like when you're in class, you could have already done it, and we can talk about it. But since I didn't mention this before, today you have up until the end of the day to turn it in. So in going over the homework, we're going to talk a little bit about organizing code into functions. We're going to see some interesting functionality in SciPy and so forth. And then we're going to use that code to learn about two tools that I mentioned briefly towards the end of class last time, which is the Python debugger and the Python profiler. So these are some incredibly useful tools for figuring out where your program isn't working correctly, if it isn't working correctly, and also figuring out where your program is slow if your program is running too slow. And then towards the end of class, we're going to introduce homework 2, your next homework assignment. Okay, so let's just begin by going over homework 1. And for today's discussion, I'm going to switch from using IPython notebooks to using the IPython interactive interpreter, just because it's a little easier. It's a little easier when we're talking about executing large files of code, which is sort of the kind of file that you turned in for your homework 1 solutions. So let's read over my solution here. and I'll ask you a few questions along the way. So at first, I import the key modules here, so SciPy, Matplotlib, and Matplotlib PyLab. This next module, PDB, is the Python debugger. We'll talk about that a little bit later today. So these first two functions are we're going to use later in class today. So let's just skip them for now. And take a look at the first function here, which is a function that's called compute distance. And it takes a point, it takes the x-coordinate and y-coordinate of a point, and computes the distance of each box from the point that you passed into the function. And it's going to return that array. So in this function is wrapped up some of the code that you need to answer the first few questions and create the first few plots in the assignment. In particular, we started by computing the distance from 0, 0, and then we were asked to compute the distance from 5, 5, right? So whenever that happens, whenever you sort of first need to do some operation with 0, 0, and next you need to do it with 5, 5, that's an indication that you should probably encapsulate that into some code that you can call again and again using different arguments, right? So in this particular case, I've encapsulated in a function here that takes 0, 0 by default, and you could pass in 5, 5 otherwise. So a couple of notes here, and I looked through some of the code that those of you that turned in the assignment have already turned in. So my first note is some of you imported NumPy as well as SciPy, or just NumPy or something like that. So SciPy, when you import SciPy, it actually imports NumPy already. So SciPy.array is exactly the same as NumPy.array. And so there's no need to import NumPy, basically. I always just import SciPy and work from there because SciPy provides more functionality than NumPy does. So that's why I always just import SciPy. So the second thing to talk about is creating, yeah?
Why have you imported Matplotlib and something, the subclass of?
So this is a submodule of this module. And Matplotlib PyLab provides some useful functions like telling Matplotlib to display an interactive plot. And you'll see below in my code where I call that.
My question is, when you have imported Matplotlib, PyLab is also imported automatically?
No, it's not. So the same way when I import SciPy, SciPy.optimize isn't imported automatically. So a module can have submodules that don't get imported automatically that you have to explicitly tell Python to import. And that's what's happening here. So Matplotlib PyLab doesn't get automatically imported when I import Matplotlib. Okay, so the first thing I want to talk about is how to create that 2x2 or two-dimensional array that just counts 0 through 19, right? So this is one particular way that I've done it. So let's read this. It's called SciPy vstack. So I'm saying stack these things vertically. Index is an array that's just a range 20, so it counts from 0 to 19. And what does this do when I do bracket index times 20? So if I do bracket 4 times 20, what does that do? It repeats 4 20 times. Okay, so the multiplication operator on a list just repeats that list many times. And so that's what's going on here. I'm repeating that array 20 times, and I'm saying stack those vertically. So that's going to give me the x's. But there's tons of ways to do this. So I'm curious, for some of you, can you tell me your way that you created that two-dimensional array? So you did SciPy dot tile, and what are you tiling?
So NumPy dot a range 20, comma 20, comma 1.
And then what is
20, comma 1.
20, comma 1? Yep, makes sense. Okay, so the reason I'm talking about this is because it's people figure out different ways of doing things, and it's a nice way of kind of figuring out other functionality that's in SciPy that you might not know about. So tile takes one array and repeats it in this particular format, right? So this says take this array and repeat it in 20 rows in one column, and so that's how we get our 2D array. So other methods that some of you came up with. There's probably like 5 or 6 perfectly good methods of doing it. So some other ones. Yeah.
So I directly created the coordinate array using ngrid.
Okay, so how does that work? Can you tell me?
I created an array called points equals to nt.ngrid, square bracket open, 0:20, comma, 0:20.
Great.
And then I reshaped it with brackets 2, comma, -1, and then transposed it.
So tell me what to pass into mgrid.
0:20, comma, 0:20. Square bracket? Square bracket, yeah.
All right, right, okay.
And then I reshaped this to 2, comma, -1 and transposed it. So
2 comma, reshape to 2 comma
-1.
-1? And then you transpose this?
So it gives you a list of all the coordinates that we need.
Okay.
And I use p this on this to calculate the distance of each point, and whenever you enter
So this isn't doing what, so it does compute all the points, absolutely right. It doesn't do it in the way that we talked about, right? Because you never create the X array that has all the X coordinates in a 2x2 array. But perfectly fine way of computing all the distances. But can you not use mgrid to actually create the X array as well?
before reshaping it, you create the X array and the Y array separately. The Y and the X.
I see. So what does .mgrid do in general? It returns a dense multidimensional mesh grid. Okay, so here's an example. Okay, so I guess it does actually, it creates the X and the Y arrays. So to be more precise, you could have done something like this. And then, that's our X array, and then that's our Y array. And I might have done it the opposite way, right? So Y, X, right? And that would create the 2 arrays that we're talking about. Fantastic way of doing it. Like, really nice. mgrid's probably super useful. I haven't used it that much in the past. Other ways that you created this. Okay.
I created I just had the one array, 0 to 20.
Okay.
Get my X coordinate, I just multiplied that by 1, 20 by 20.
Yep.
And then to get the vertical array, I took the horizontal array and expanded it along the first dimension and then multiplied that by 4 lines.
Yeah, so this is a great way to do it. So something like that, right? So you took SciPy 1s, you multiplied it by a row vector to get all of this. And to get the column vector, you have to expand dims on A, and you'll be multiplying by a column vector, so you'll get the zeros on the top. Yeah, perfectly fine way to do it. Other people did something similar, except with zeros in addition instead of 1s in multiplication. Also perfectly fine ways to do it. Okay, so great. All really useful. So let's see what else is going on here. So this is something that most of the people that I saw had something very similar. So I took the X coordinate, subtracted X from it, the Y coordinate, subtracted Y, squared, and then square rooted all of that. So what we're using here is the fact that SciPy does broadcasting, right? So I'm taking a scalar and subtracting an array from it, and what that's actually doing is subtracting that or each one of the elements from that scalar. Make sense? Okay, so let's take a look at this, and this is a little bit different. This function's a little bit different than what most of you did. So most of you, in one of your functions, you put in something like a matplotlib IamShow. Also, many of you in that function had a couple of parameters at the top. So one was for the color map, and the other was for the interpolation method. And you took those two parameters and you passed them to IamShow. Okay. So how is what I'm doing different than that? Yeah, and so what I'm doing is I'm actually like any argument that IamShow takes, you can pass into this function. Okay? So not only CMap and interpolation, but whatever other arguments IamShow takes gets stuck into keywords argument. Over here, I've also added an extra argument in there called CBar, right? Do I want to plot the color bar or not? By default, CBar is going to be false. Here I check, is CBar in the keywords argument? And if it is in the keywords argument, then make it be whatever the person passed in. And then delete CBar from keywords argument. So why do I delete it here? It's because IamShow doesn't take CBar. And so if I passed this into IamShow without deleting CBar, I'm going to get an error that says IamShow received an argument that it wasn't expecting. It doesn't know what CBar is. Okay. So here I've taken out the arguments that my function wants to take, and everything else got passed down to IamShow. And you'll see that a lot of GeoPlotter is written in the same way, where you can pass in all kinds of functions into the underneath whatever matplotlib base map takes. Okay, so then it's IamShow the values array, so all of you guys did that. And here are some if statements that work based on this color bar. So if the color bar is true, then I'm going to add that matplotlib color bar that was for the last image. And then over here is just some if statements to either interactively show the picture or save it. Okay, so if somebody passed in a file name, then I'm going to save it using savefig. We're going to talk about this in a moment. And if they didn't pass in a file name, so if file name is none, which is by default, then it's going to interactively pop up the display. Okay. So save distance plot is just takes in a file name and a point. It computes the value. So this function basically combines the two functions that we've created so far, right? One computes the values, and the other saves a plot once we actually have the values. So all this function does is take a point and a file name, computes the values based on that point, and then saves that to a particular file name.
Why is there a star on point for...
Fantastic question. Why is there a star on point? So no, let's take a look at compute dist and how this particular version of compute dist is written. So what does it compute dist take? It takes two arguments. That's the x value and the y value, right? And so what should point be? So it's a tuple. It's actually just two, a list of two values, but it shouldn't be like many two values, right? So in particular, what I mean is like this is okay, but this is not okay. Right? So if I pass in the first one, what does the star do again? We're just going to split them out into the two arguments. So it's going to pass the x-coordinate into the x and the y-coordinate into the y. So that's what the star is doing.
You used a transpose earlier.
Yep.
And then copy it.
Yep.
And I couldn't figure out how to get, when I had the list that was horizontal and I just tried to say y equals x dot t or whatever, that doesn't just turn it into a...
So say again?
So I remember when I was trying to say I had x and I already had a row vector of 0 to 19. And then if you just say y equals x dot t, it just gives you back x. So you have to...
What do you mean it gives you back x? So here's my x, or...
Well, if you just had x was the row vector and not the whole array.
Let's say this is my x. This is my row vector. Oh yeah, if you do a dot t, you're gonna get the same thing. And the reason is that a shape is 10, and what transpose does is it flips the first two indices. And since this array has only one index, dot transpose does nothing.
Okay. All right. Thank you.
Okay, so let's see what save minimum distance plot does. So it takes in now a list of points. It starts with value equals none and iterates over those points, computing the value for that particular point. If value is none, it sets it equal to whatever I computed, and otherwise it computes the minimum between value and cval, right? So that's how we're going to create like the last few figures in the assignment, that we have lots of points and we want to take the minimum distance between all of those points, right? Okay, so many of you, and I looked at several homework assignments, so many of you did something similar. A few did something slightly different, so any suggestions on like what you might have done that's different? Okay. Yeah, so great in terms of writing a class in the following sense. And the code that I'm showing you is only using functions to organize the code. And if you remember from a few lectures ago, there were really three ways of organizing code. One was functions, the other was classes, and the third was modules. And so what class did you write, and what data? So a class stores data and associated functions. So what's the data that your class had, and what associated functions did it have?
Functions were somewhat similar to this.
Yep.
Every image I thought of it as an object because everything
Yeah.
has different parameters.
Fantastic. Okay, so like your class would have the data in it would be basically the value that you're going to be plotting. It would be like that 2D array or whatever. Yep. And so it would have some functions that created the values and some function that then plotted out the image. Like that's a fantastic way of organizing this code. In fact, I would say much better than the functions that I'm showing you, because classes generally are much nicer to think about than a bunch of functions. Other comments in terms of how to do the minimum distance plot? Okay, so I have one, which is so there's a for loop there, right? I'm iterating over all the points to find the minimum distance. So yesterday I told you that if any of you figure out how to do this without a for loop, we can talk about your code. So I spent a little bit of time thinking about it, and I'll show you a way of doing it without a for loop. Okay, so let's take a look at this similar function, so save minimum distance plot, but this time no for loop. Okay, so the first few lines are quite similar. So we take our points array. So points array lists things like the first point is 0, 0, the next one is 5, 5, and so forth. And now it's going to turn it into an array that has n rows, so as many rows as I have, in 2 columns, because the first column is going to be the x coordinates for those points, and the second is going to be the y coordinates. So next here, we create the same x and y arrays in whatever method that you like to create it. So this is the x and the y arrays. And now let's see how values is computed. So to compute values, I'm using essentially the generalization of of subtracting a constant from an array. So let's just look up SciPy broadcasting. So if you look this up online, there's fantastic documentation for it. So these are the general rules. So when operating on two arrays, NumPy or SciPy compares their shapes element-wise. It starts with the trailing dimensions and works its way forward. Two dimensions are compatible when either they're equal or one of them is 1. Okay? So let's see some examples of this. So before we go to their more complicated examples, let's do some similar examples. So let's say, or some smaller examples. So things that we've seen. So let's say A is 10 by 10. And little b is just a 10, so it's just like a row vector, right? So if I do a minus b, what we've seen happen is from every row of a, we're going to subtract b, right? So why is it doing this? It's because it's lining up these shapes. So a is 10 by 10. And b is 10. And so what it's doing is repeating that b for all the rows of A. Does that make sense? So similarly, if c is a constant, right? So it's a constant, so just 1. And I do A minus c, for A minus c, I have here a 10 by 10. And c is just a 1. So it's taking that c and copying it for both the rightmost dimension and then the leftmost dimension, and so forth. Does that make sense? Okay, so this works for regardless how many dimensions your array has. So here's an example. So maybe you have a 3D array that's 256 by 256 by 3. So the reason they did this is because images often have a red, green, and blue value. So that's the 3. And this is the pixel index, like 256 rows and 256 columns. And I have some particular color I want to add to all the pixels, right? So some red, green, blue thing. And so if I take this 3D array and add this 1D array, the result is going to be 256 by 256 by 3. So everything worked well because the last dimensions matched up, and it gets repeated, like this array gets repeated 256 by 256 times in the first two dimensions. Make sense? And similar for much more complicated broadcasting. So here's one array that's 8 by 1 by 6 by 1, and another one that's 7 by 1 by 5. And so what's going to happen is in the last dimension, this array is going to get repeated 5 times. In the second dimension, this array is going to get repeated 6 times. And in the last one, this one is going to get repeated 7 times. Does that make sense? And so let's see how to use this to compute that minimum distance without a for loop. Okay? And so here's the computation. Let me make this slightly bigger so you guys can read it. Okay, so it looks very similar as before. We're going to take the square root of x coordinates minus, so the points x coordinate minus our x, the points y coordinate minus our y. But I want to do it in such a way so that the broadcasting essentially does the for loop for me. Okay? So let's read what this is doing. So what kind of an array is points colon 0? So points was n by 2, and so points colon 0 is going to be what kind of an array? It's just n, right? So it's just n, because it's going to take just the 0th column of points. So that's what this says. So points is just n. Okay, so x was 20 by 20. And so what kind of dimension do I want on x to make sure that x gets subtracted from each one of the points? So you can read the documentation here. So I've made it to be a 20 by 20 by 1. Right? So what's that going to do? It's going to take that X array, and it's going to repeat it n times, and it's going to subtract each one of those from each one of the points that I listed. Does that make sense? Okay, so that's why I have an n array minus a 20 by 20 by 1, and the result of that is going to be a 20 by 20 by n. Make sense? So similar thing for the y. In fact, exactly the same thing. We have an n array. I used expand dims to make it a 20 by 20 by 1, and when I do the subtraction and the squaring, I get a 20 by 20 by n. So now these two arrays, after the squaring, they all have the same size, right? And so I can add them, and it's going to add them element-wise. Okay, so the result is a 20 by 20 by n after I add it. So now what operation do I need to do to get my final minimum distance plot? Yeah, minimize in the third dimension of the array. And so that's what this is doing. So values is that 20 by 20 by n, and in this next line we're taking the minimum along axis 2. So the axes have indices 0, 1, and 2, and I want to take it over all of those endpoints. So we're going to run some speed tests on these two, and it turns out that this one is about 3 times faster than the previous one. Okay, maybe more on this laptop. At least on my other laptop, it turns out to be about 3 times faster. And so this is an example of something that people in MATLAB often call vectorizing. That term also sometimes translates into Python. But the punchline is avoiding for loops makes your program faster. But oftentimes the expense is more memory. In particular, what's the difference between this function that I've written and the function before that? Is that if you look at this one at all times, at most it stores like 2 20 by 20 arrays, right? Because it's always taking the minimum of the new one that it computed. So the maximum memory usage here is 2 times 20 by 20, right? But what's the memory usage on this one? It's, yeah, n times 20 by 20, right? So if I have like 10, if I pass in 10 points, this is going to use 10 times 20 times 20 memory, right? Whereas the other only uses 2 times 20 times 20. So there is this trade-off. The trade-off is you use more memory, but you gain speed in terms of your computation.
Instead of using a function, scipy.minimum, how many ever times, 5 times I guess, there is a scipy.minimum.reduce that takes in multiple, an array of matrices and gives the minimum. So we are just using the for loop just to create those Euclidean distance matrices.
Oh, so you could do that. So what you're saying, you're suggesting a yet third way, which is having the for loop here and appending these all these ones into a list, and then using that scipy.minimum function to sort of compute the minimum between them. So that works perfectly fine. It's going to produce the right answer, but it's kind of like the worst of both worlds because it both uses n times 20 times 20 memory because your list is going to have those 20 things, and it has the for loop of creating those one at a time as opposed to using the broadcasting, which does it without the for loop. So in general, I would suggest, if you're using a for loop, oftentimes people call this method of writing a program, they call it using an accumulator, okay? So that's kind of a fancy term for it, but all it is that I have the answer and I'm going to build up the answer a little piece at a time, sort of take the minimum at each iteration of the for loop. And the reason that you want that people do that is because it saves on memory. Like that's really the only one. Okay, so now you know a little bit more about broadcasting, and so let's see. The code in here, all it does is it calls those functions to create the various plots in the program. So, for example, calling save distance plot with 0, 0 creates the first plot. You can call it with a different interpolation, and that interpolation is going to get passed down into IAMShow, and it's going to look different in terms of the figure. Okay, so any questions about the homework solution in general before we move on to talking about the Python debugger and profiler?
How to say this name if you could.
Okay, so what does this do? What this does is it allows you to execute your Python file from the command line, okay? So let me just for a moment comment these out. And let me comment this out as well. And let me just add one statement here, like print hello world. So now when I execute that file from the command line, what it does is it's going to execute all of the commands under that if statement. And what that if statement is saying is that it's basically saying, did I get executed from the command line, or did someone import me? Okay. So so this is different than import homework 1 solution, right? So now when I imported, I didn't get the hello world. That print statement didn't get executed. But all the functions are in here, right? So for example, save minimum distance is in here because that got read when I did the import. Does that make sense?
Is it like your homework's a module now?
Oh, that's right, yeah. So any .py file you can turn into a module just by putting it in the current directory and then importing it. Okay, if there's no other questions, let's spend a little bit of time. Yeah.
And when I use IPython, I can use the percentage symbol with the matplotlib notebook.
Okay.
I cannot still use it.
Right, because you're not in the web interface. Like, so if you plot here, so if I plot something here, it basically is always going to show up as an interactive plot. Right, so that's the kind of interface you get as opposed to getting embedded in there.
One question.
Yes, question.
So, when I was looking for appropriate functions online, and in some of the stack exchange answers, they use np dot some function. And
so np is usually a shortening that people have for numpy. So what people do, and this is syntax you could use, but it's generally frowned upon, is you could do import numpy as np. So what that does is it imports the module, but it immediately renames it to this as opposed to that. The reason that I suggest to not do that is because you might call it np, some other person might call it npy, right? And then it's like really hard to know what module you're actually using. So the general rule of thumb is just like use whatever the actual module name is. That way when people see your code, they know exactly which function is getting called by your code. Okay, so let's talk about the Python debugger. So broken function is a function that has a purposeful bug in it, okay? So it just takes 1 and divides it by 0, and that's going to give me a division by 0 error. But it could be sort of any error that actually throws an exception that you might have. So let's take broken function and stick it inside of compute dist. So right in here, let's stick in broken function. And then let's say that here we are, we're in IPython, and let's say that all I want to do is save the distance plot for 0, 0, okay? So the way I can run the file from inside of Python is just with the run command. So you could just go run -I homework1 solution. And what that does is it actually executes that file as though name equals main. So it's going to run everything under the if statement. And in particular, what it's going to do right now is call that save distance plot function. Okay, so here it is. And so I got an error. And it's a nice error, division by 0 and so forth. But maybe it's some kind of more complicated error, and it's hard for you to figure out what it actually is doing and where that error is happening. So in the Python interpreter, one thing you could do is type %debug. Okay, so % is a special command, or means a special command. And when I do %debug, what that does is it drops me into the part of the code that actually caused the error. Okay, so over here I was in the interpreter, and now with this little printout, you can see that where I am is I'm inside of broken function and at the particular line that caused the error, which is the 1/0. Okay. So an IPDB stands for the Interactive Python Debugger. Okay, so the prompt changed, and that's how you know that you're in the debugger. So if you type help here, it'll list a lot of commands that are available in the debugger. So break, condition, disable, ignore, so forth. And you can read a lot of these, and we'll use a few of these in just a moment. But so some of these are can be quite complicated if you haven't used debuggers before. But one useful one is L, or list. Okay, so it appears there. And I think if you type help L, it's going to tell you what it does. So L is list the source code for the current file. So without arguments, it lists 11 lines around the current line. Okay, so when I press L, it can tell me sort of where in the file am I right now in terms of this execution. Another useful one is U, or up. So it says move the current frame one level up in the stack trace. So for those of you that haven't had much computer science before, like there's a lot of jargon words here. So let me just spend a few moments to explain it to you. So let's just imagine that I have a function A. So and in here, it just does nothing. And I have a function B, or maybe inside of A, I just say x equals 7. Inside of B, I do x equals 10, and then call A. And inside of C, I say y equals 5, x equals 3, and then call B. Okay, so 3 functions. And then suppose that I execute C. So executing C is going to start us here at the top of C. It's first going to create a y variable, set it equal to 5. It's going to create an x variable, set it equal to 3, and then it's going to call B. Okay. So the way that this works inside of the computer's memory, so here's a picture of memory, while the program is running. First, the computer is going to create a little space of memory that's specific for the very first function that you call, which is C. And in that piece of memory, it's going to put x is 3 and y is 5. Okay, so that came from C. As soon as C calls B, the computer is going to create another piece of memory that's for B's variables. Okay, and in that, we're going to get x equals 10. And as soon as B calls A, we're going to get a little space in memory that has A's variables in it. Okay, and then when A returns, we're going to walk back up this stack. So people call this the call stack. And each one of these little spaces of memory that are associated with a particular function is called a stack frame. Okay, so and that's why the various x's here, they don't kind of trample across each other, right? So when A does x equals 7, it doesn't somehow affect the value that C created for x. Okay. So going back to our debugger here, so U is move the current frame one level up in the stack trace. Okay, so what is that going to do? So if I press U, it moves me up one level to the function that called broken function. Okay, does that make sense? So broken function got called from, and let's maybe, it got called from compute dist. Okay, so maybe my error is not actually in the function that caused the error, but in some caller, because the caller passed in the incorrect arguments or something like that. So using U, which stands for up, and D, which stands for down, lets you walk up and down all the memory of all the functions that are getting called up till now. Does that make sense? Okay, so now I'm at this compute dist function. So one thing I might really care about is, wait, so like what are actually the values of the input arguments to this function? So one thing you could type in here is args. And by printing args, the debugger is going to print out all the stuff that this function got called with, okay? But you could do all kinds of other cool stuff. Like you could do print point x minus point y. So I can do just like inline computation, interactive computation with all the variables that are in that function at that point to sort of check out like, hey, what's exactly going on here? Like, why am I actually getting this error? So, for example, one useful thing is like maybe I want to figure out what shape is this array? Like, is it the shape that I expected it to be? Like, is it really 20 by 20? Does it really have the contents that I want, right? So these are the various distances that got computed, right? And so, one check I might run with the debugger is, yeah, like these distances seem right? So like this guy is 1 away from 0 because just on the x-axis, distances are easy to compute. You can do that in your head without square roots. Okay, so those are the most common things that I do with a debugger is basically walk up and down the stack frame looking at various variables or doing inline computation, potentially looking at arguments and other things. By the way, so you can also do things like other inline computations, like let's see, temp equals value minus 4, and temp equals temp squared, and maybe print temp 0. And so that can also be very useful, right? So what you can do is basically arbitrary computations, introducing like new variables if you want. You can call things like, let's say, so you can call various SciPy functions is my point. So maybe just, let's do this. Okay, so it takes like the exponent of value. So regardless whether it's your function or some built-in SciPy function, you can call it inside the debugger to actually see what's going on. And then whenever you're done debugging, you can just press Control D, and that pops you back out into the Python interpreter where you can run things again. Okay? So let's say that I identified my problem here, which was broken function, and so I can delete broken function, and that works. So sometimes you want to purposefully cause a bug in your code so that you can step through particular lines of your code. Okay, so let's say that I'm down here, and it's my first time using all of this broadcasting stuff. And so I want the debugger to kind of drop me in here so I can go line by line through all of these computations to make sure that each one of them is doing exactly what I thought it should be doing, okay? So the way to do that is to import PDB, and you don't have to do it at the top of the file. You could do it right where you want to debug. So you could do import PDB and then pdb.setTrace. And now let's change the call here so that it's actually calling the function we want to call. So all I did here was I just made a call to save minimum distance plot no for loop with various parameters in there, okay? And so my goal is that when that function gets called, I hope the debugger is going to stop right here so I can walk through all of these lines and look at the values of all of them, okay? So back in the interpreter, I'm just going to run that file, which is going to go and execute that function call. And what happens when I call run this time is instead of going through the whole program as it usually does, is right where I called that set trace at the next line, I got popped out into the debugger, okay? So now I can do the things that I showed you previously, like list lines, and so that's going to show me the function that I'm in. So that was the set trace, and that's where I am. And now I want to step line by line through this program to figure out exactly what's going on. So the things to help you there is S, which stands for step, execute the current line, stop at the first possible occasion, either in a function that's called or in the current function, okay? And the other one that can help you is N, which stands for next. Continue execution until the next line of the current function is reached or it returns. Okay, so how are these two different? How is step different from next?
Because a function, it goes to the function.
That's right. Yeah, so step, the way that I think about it is if there's a function call, I'm saying I want to go inside that function call and figure out what's going on inside that function call. While next says, if there's a function call, I actually don't care about the function call. Just execute this line and move me to the next line of the current function. Okay? So let's do some of that. So let's go next. Now points is created, so I can do things like print points. Okay, so there's my points. It's a 2D array. I could do print points.shape. It's 5 by 2 in this particular case. So I could do next, which is going to go into VStack. So, by the way, like most all of your modules here, like scipy.vstack, all the code is actually like on your laptop. So if you wanted to go see what scipy is doing, like you could say S, which said step, right? So when I said step, what that's going to do is take me inside of VStack. So now I'm inside of the scipy code that actually does like all the stacking of the various arrays. So then I pressed up, which takes me back up to the previous stack frame. Okay. And then you could also type continue, which continues execution, and stop only when a breakpoint is entered. And there's probably, continue execution until the current function returns, right? So I press down, I'm back in VStack. Let's say I'm satisfied with the way that VStack works. So then I can just go return, which is going to pop me back out into my function, which was where we're creating the x's and the y's, okay? So I hope that you realize how tremendously powerful and useful this is. because most of the time when you're trying to figure out where the bug in your code is you're essentially trying to run that code in your head, right? You're thinking, okay, well, this line's supposed to do this line's supposed to do this. With the debugger, instead of running the code in your head, you actually get to run it on the actual computer and interrogate the results to make sure that they actually match up with what your thinking is, okay? And so if I type continue, it's going to go through the rest of the program, executing and plotting out the results, okay? Okay, so let me maybe show you a couple of other things. So again, we're dropped into set trace. So one useful function is locals. So locals basically prints out all of the memory that's associated with local variables in this function, right? So in particular, value was a variable we created, and it was at the beginning of the function, and I set it equal to none. So it's a little dictionary. Value gets mapped to none, index got mapped to this array, keyword args is all these things, and then points is this thing. And PDB is a module that I imported. So when I imported it, it created a little local variable for it, okay? So locals is nice if you want to just figure out what are all the variables that are defined right now, okay? Okay, so one other thing that I saw in some people's code is the following, which I'd like you to avoid. So so let's say that x equals 5, and then I do def a function, and then return 7 plus x, okay? So this in Python is going to execute perfectly fine, okay? It's not going to complain that x is not known here. Because what Python does when you put in a variable name is it goes through that whole stack trace looking for the most recent place where that name is defined, and it's going to use that one, okay? But the reason this isn't good is because if this doesn't get executed first, then you're going to get an error, okay? So the main takeaway from here is that all of the variables that you use inside a function should typically be either passed in as parameters or defined within the function, okay? So using a variable that's defined outside of a function is possible. Like Python will let you execute this, but it's terrible in terms of debugging both your own program and other people's programs. So generally try to avoid this. There's going to be maybe a few times when we do this, but it's going to be rare. Okay, so the next tool that I'd like to show you is the Python profiler. So remember how we have these two functions. So one does the for loop and the other does the broadcasting for computing the minimum values. And I want to figure out how fast are these things, and like if they're slow, where are they slow, okay? So let's go back to the two functions. So here they are. This one was the one with the for loop, and this one was the one that does broadcasting. And just for a moment, what I'm going to do is just comment out the actual plotting, okay? Because, so the reason I can feel comfortable commenting that out is because it's the same in both of the functions, right? They both call the same function for plotting, so like none of the speed differences should be coming from there, okay? Okay, so for figuring out where your program is slow and figuring out how to make it faster, the thing that you can look up online is the Python profiler. And both the words debugging and profiling are common words. So in the sense that if you sort of decide that you really don't want to do Python, but you're going to do MATLAB from here on, MATLAB also has a debugger and a profiler, okay? So the same things that you can execute here, you can execute with other languages. They just happen in a slightly different way, okay? So it's useful to know that debuggers and profilers exist in general. But, so what are the Python profilers? There's two of them, cprofile and profile. cprofile runs a little faster, so we're going to use that one. And then this is some examples of profile. So you're going to import, we can import the module here and then run some code. So in particular, what they're running here is the compile function in the regular expression module. And then it's going to print out some stats after we run that. Okay, so the important thing for us right now, before I actually do an example, is to understand what some of these columns mean. Okay, so the columns are ncalls, which is the number of calls for a particular function. So each one of the rows in this output stands for a function. This is the compile function in the RE module, another function in the RE module, function in a different file in SRE, and so forth. Okay. So the first column is the number of times that function got called. The second one is the total time spent in the given function, excluding time made in calls to subfunctions, right? So I have one function and it might call lots of other ones. I might want to know how much time am I spending just in this one, and don't count like the subcalls. Per call is just divides these two things. And then cumulative time is the cumulative time spent in this and all subfunctions from invocation till exit. So cumulative time includes the subfunction calls as opposed to excluding them. And there's another division that divides the cumulative time by the number of calls, and then it prints out the file name. Okay, so let's see. Let's execute this on our file here. Okay, so let's read these few lines. So I'm importing cprofile. So pstats is a module that allows you to print out that table of statistics for the different functions in different ways. So we're going to work with that a little bit. So imports the profile module, imports pstats, and let's see what I'm asking the profiler to run. I'm saying run save minimum distance plot, no for loop on all those points. But I want to run it several times because it takes very little time, and so I want to sort of get an average over several runs. So maybe I want to run it 10 times as opposed to just once. Okay, and this probably won't make that much of a difference. And the last parameter here says save all the statistics on how fast each of these functions are running into a file called profilestats.txt. Here I'm loading these statistics, and then we're going to sort them. So let's run homework 1 solution. Okay, so my PDB call is still in there, so let's remove that. And let's take a look at some of this output. And in particular, let's read about what this last line is doing. So it takes the statistics from the profiler, and you can sort it based on a particular column. So here I'm sorting it by total time, but maybe what I'm more interested in is in cumulative time. So let's say I want to sort it by cumulative time. And then print stats says how many functions do you want to print. So here I'm saying print 10 of them. So let's see what this does. So I want to sort the stats based on cumulative time and print the stats for 10 things. And so overall, the cumulative time over 10 calls of this function is 0.002 seconds. Okay? So really kind of fast. And here you can see that it calls various other things. So for example, it calls reduce of numpy ufunc. it calls min from numpy, ND array, and so forth. So let's compare that to, so let's remember this, so 0.002 seconds for no for loop. And let's see how fast the other one runs, which is the one that does use the for loop. And I'm just going to do it here. So I'm going to do it by just rerunning my file instead of cut pasting. So that one, the cumulative time in save min distance plot was 0.009 seconds, right? So the one where we did broadcasting was more than 3 times faster than the other one, more than 4 times faster, actually. Right? So broadcasting can save you a lot of time. So let's do one more thing, which is over here I have like some really slow function. Okay, so it's a slow function, and all it does is it creates a list, and then 100 times it walks through the list to almost the last element of the list. So just like a really slow function. And let's say that it's hidden somewhere inside my code. So let's say that I go down here in the one with for loop, because that's the one that we're doing. And, in here I have like a really slow line in my code. And I want to automatically use the profiler to figure out that that's the place where I should really be optimizing my code to make it run faster. So I ran the same code. So we're starting by cumulative time, and you can see that the cumulative time in save minimum distance plot was 0.25 seconds, and the cumulative time in slow function was 0.24 seconds. So by doing this sorting, it's basically automatically boiling up to the top the functions that are the slowest in my code. So now I know that if I really want to make this faster, what I really have to do is go and edit slow function as opposed to some other function that's inside my code. Okay? So one last thing I want to show you about profilers and is that typically people build quite interesting visualizations for the profile results. So there's one called SnakeViz. It's just a separate program that you can install on your computer. And what you pass into it is that file we created with all the profile statistics, okay? And it's going to pop out something like this. And this is basically just a nicer way of going through all the information that I printed out in the table over there. In particular, here's the table, cumulative time per call and so forth. So we can sort by cumulative time, and that shows you that slow function is the slow one. And then in terms of this picture, if you sort of scroll over things, and let me make it slightly bigger font so you guys can read, in the middle is kind of the whole program. So the whole program takes a cumulative time of 0.25 seconds. That's 100% of the time. One line out of that is basically all of that time is in save minimum distance plot, which takes almost all the time. So just 0.08% of the time isn't in that function. Where is that 0.08% of the time spent? So, any ideas? Where is that 0.08% of the time spent? It's because I called that function like 10 times, if you remember my code, right? So let's go back and look at what's going on here. over here I have just a little implicit for loop, right? I'm taking on a list, and I'm going to create that list, or I'm going to execute this 10 times because of this for x in range 10. I've shown you this before, have I not? List comprehensions, they're called in Python. Right, so this is like an implicit for loop. So that 0.08% of the time is taken in here, in that, like going over that for loop. Okay, so here we are, that was save minimum distance. And most of save minimum distance's time is spent inside a slow function. Okay, so slow function takes 95% of the total time of the program. And then if you scroll here, you can see that a little bit of the time of the overall program, about 4%, is taken by compute distance. Okay, and compute distance itself calls various functions. And that's what this whole slice of the stack is. It's showing you each of these functions, how their time is broken down into all the different pieces that they call. So if we look at compute distance, it calls vstack, it calls square root, and it calls, and some of it is spent inside of compute distance itself, right? So by the way, you can also zoom into this by just clicking on this. And so now the center is compute distance, and then this is vstack and so forth. So now if I really wanted to optimize my program, what I could do is go through the several options that you guys gave me for creating the X and Y array. Because like maybe the mgrid one turns out to be 100 times faster than vstack. Like that's possible, right? So if like this is getting executed thousands and thousands of times, maybe I want to switch to mgrid as opposed to vstack. Okay, so questions about debugging or profiling?
So, can I say we can only use this profiling when we are when our code is function?
Oh no, this works perfectly well with classes because each class method is itself a function.
Yeah, so what if my whole code is no function, just line by line?
Oh, so there are other profilers that can be done line by line, but typically those are slower, and that's why they're not built in.
Okay.
But Python has modules for those as well. And so if you look up line profiler, usually that's what they're called, there'll be other tools that can do that line by line as well. So I'd like to spend the last bit of class here introducing you to the next homework assignment. So it's posted online. It's due next Thursday. And let's just briefly read over it. So in this homework assignment, you're going to learn, you're going to get to do some things with pandas and matplotlib base map. In particular, you're going to do some geographic plotting. So the first thing you're going to do is you're going to use GeoPlotter to create some maps of the world, and then you're going to download an interesting data set. So this data set is from a series of papers that some economists or political scientists have read that in some particular way they compute an index about how influential a particular country is in a particular year. Okay? So in this data set there's tons of years and tons of countries and various data about those countries, and one piece of data is this index on how influential the country is. Okay? So then you're going to write some code to play with that data, and you're going to download a shapefile for these various countries. And by following the steps here, 1 through 5 or so, you're going to now create a class. So no longer are you going to create functions. You're going to create a proper class to do these things. This class is going to be derived from the GeoPlotter class. Okay, so derived from means exactly what we saw a few days ago in class, where we started with a Mazda, but then we created a turbo Mazda. So you're going to add some functionality to GeoPlotter by creating your own class on top of it. Okay, and so this describes the various methods that your class should have. And at the end, you're going to create a movie, and the movie is going to look something like this. So all it does is it goes through the various years, and plots the various countries of the world based on their influence index in this database. Okay? So you're going to work with both geographic plotting to do all the polygons correctly. You're going to work with matplotlib to add this particular notation to the plot. And then you're going to create a whole bunch of, like each of the individual frames of this movie, and you're going to combine all the frames into a movie using either the command I provided in the description of the homework, or any sort of movie editing software that you know of. And the reason I want you to create this movie is because in the past, this has been tremendously helpful for me in terms of presentations, both to companies or to various other academic groups, to sort of show a movie-based visualization of perhaps some algorithm or method or some solution techniques that you have. And so combining individual pandas or individual matplotlib plots into a movie is something useful. And so what you're going to turn in at the end is your homework.py file. You're going to create the actual movie and a short explanation the same way that you did with the first homework assignment. Okay, so significantly more difficult homework assignment, I would say, than the previous one. And so in general, they're going to get more and more complicated as we go forward in class. So I suggest take a look at it as soon as you can to be able to kind of budget your time to get it done by next Thursday. Okay, thanks a lot for listening, and I'll see you all next week.